Good morning, students. Now we'll study about Module 4, Theory of Simple Bending. In this chapter, we'll deal with normal stresses in beams. So we have to study about the theory of simple bending. That is, the bending is always associated with shear. Now we have seen in the previous chapter that the bending moment and shear force vary from section to section on a beam when it is subjected to external load. To resist the bending moment and shear force, the beam section develops stresses. Okay, we are interested in finding out what is the stress developed on a beam section. The stresses due to the bending moment and due to shear force are determined independently. So first we'll deal with finding out the normal stresses in beams. So what is theory of simple bending? Bending is usually associated with shear. However, for simplicity, we neglect the effect of shear and consider the moment alone to find the stresses due to bending. So such a theory which deals with the finding of stresses at a section due to pure moment is called simple bending theory. So all of us know whenever a beam is subjected to a moment, the beam will bend. So due to this moment, the beam sags or hogs. Okay. So it is obvious that due to sagging moment, fibers at bottom get stretched, and hence we can say at lower side elements are subjected to tension, and on the upper side the fibers get compressed, and hence an element in the upper portion is under compression. So this is the case of hogging moment. Now, thus due to bending moment, tensile stress develop in one portion of the section and compressive force in the other portion of the section. So in between these two portions, that is the compressive portion and the tensile portion, there is a layer where stresses are zero. Such a layer is called the neutral layer. So its trace on the cross section is called neutral axis. The layer on which there is no tensile or compressive stress is known as neutral layer, and the intersection of this neutral layer with the cross section of the beam is known as neutral axis. Now we'll see what are the assumptions in the theory of simple bending. So it is also known as pure bending theory. What is the meaning of pure bending? Pure bending means you consider this double overhanging beam. So whenever you draw the bending moment diagram and shear force diagram for this beam, you can see that the portion dB is subjected to shear, which is equal to W, and this portion AC is also subjected to a shear, which is equal to W. Now if you draw the bending moment diagram, the bending moment diagram will be like this. Now we can see that in the portion DC there is only bending, no shear. So this portion is subjected to pure bending. So this theory is applicable for only pure bending case, that is no shear force case. The theory which deals with finding the stresses at a section due to pure moment is called simple bending theory or theory of simple bending, which is not subjected to any shear. So whenever a beam is subjected to moment, the beam sags or hogs. When it is subjected to sagging moment, the upper fibers will be subjected to compression and lower fibers will be subjected to tension, and in between there is a layer where there is no tension or compression, and the intersection of this neutral layer with the cross section of the beam is known as the neutral axis. Now if it is subjected to a hogging moment, the top portion will be subjected to tension and bottom portion will be subjected to compression, and there is a layer in between this top layer and bottom portion, that is known as neutral layer, and the intersection of the neutral layer with the cross section of the beam is known as the neutral axis. So what are the assumptions in simple bending theory? The beam is first assumption is the beam is initially straight and every layer of it is free to expand or contract. Second assumption is the material is homogeneous and isotropic. Homogeneous means there is uniformity of structure. Isotropic means uniform physical properties in every direction. Now third assumption is Young's modulus is same in tension and compression. So that is tensile stress by tensile strain is equal to Young's modulus, and compressive stress by compressive strain is also equal to Young's modulus. Now the fourth assumption is stresses are within the elastic limit and the material obeys Hooke's law. So stress is proportional to strain, and the ratio of stress to strain is known as Young's modulus. Now the fifth assumption is plane section remain plane even after bending. For as per this assumption, if you have a plane section AB, it will remain plane even after bending, that is A dash B dash. So this assumption is valid in the case of pure moment. But if shear is also associated, then shear deformations will distort the plane, and hence A dash B dash will not be plane. So this is applicable only when the depth is less than 1/10 of the span. So if the span of the beam is 6 meter, the depth should be less than 600 mm. Then only this assumption, fifth assumption, is valid. That is, plane section remain plane even after bending. Now if the span is 3 meter, then the depth will be should be less than 300 meter, so that this assumption should be valid. Now this assumption is now also known as the Bernoulli's assumption. Now the sixth assumption is radius of curvature is large compared to the depth of the beam. So if the beam curves due to the application of moment, there will be a radius of curvature, and as per this assumption, the radius of curvature is very large compared to the depth of the beam. That means the deflection will be very low. Valid if deflections are less than 1/10 to 1/5 of the depth of the beam. So this assumption is valid only if the deflection of the beam due to the application of moment is less. That is, if the deflection is less than 1/10 to 1/5 of the depth of the beam. So if the depth of the beam is 600 mm, then it should be less than 1/5 or 1/10 of the depth of the beam deflection. Okay. Now we'll see what is the relationship between bending stress and radius of curvature. So what is bending stress? Whenever a beam is subjected to some bending moment, the cross section of the beam will develop some stresses to resist this moment. So that stress is known as the bending stress. So consider a portion of beam section A, C, B, D as shown in figure. Let EF be the neutral axis and GH an element at a distance y from the neutral axis. So figure 4.3b shows the same portion after bending. So this is the portion A, C, B, D after bending. Let R be the radius of curvature and phi be the angle subtended by C dash A dash and D dash B dash at center of radius of curvature. Since EF is a neutral axis, there is no change in its length. As in the neutral axis, the stresses are 0. That is, EF will be same as E dash F dash. E dash F dash will be same as EF. The length of the neutral axis will not change. Now we can write E dash F dash by using the radius of the curve and the angle subtended as R phi. E dash F dash equal to R phi. Now what is EF? EF from this figure, it is equal to GH. Now you have written here EF equal to E dash F dash. So EF equal to GH equal to E dash F dash equal to R phi. Now we'll see what is the strain in this layer. What is the meaning of strain? Strain is equal to change in length by original length. Now this GH layer has changed its length to G dash H dash. So what is the change in length? Final length G dash H dash minus initial length GH divided by original length GH, which is equal to what is G dash H dash? This distance is R, radius of curvature, and the distance of this neutral layer to this distance of this layer GH from the neutral layer is equal to Y. So the radius of curvature will be of this layer G dash H dash is equal to R plus Y. So we can write this length as G dash H dash as R plus Y into phi minus GH is R phi divided by R phi. So we will get strain in layer GH is equal to Y by R. So if F is the bending stress and E is the Young's modulus, we can write the relationship strain equal to stress by Young's modulus, F by E. Now equating this to F by E equal to Y by R, you will get the equation F equal to E by R into Y. So we can see that the variation of stress increases with the increase of distance of this layer from the neutral axis. So F depends upon the value of Y, distance of any layer from the neutral axis. When the distance of the layer from the neutral axis increases, the stress increases and it is maximum at the extreme fiber, you can see. So the variation is triangular variation and the stress becomes 0 at the neutral axis. When Y equal to 0, stress becomes 0 and the variation can be drawn like this, and it will be maximum at the extreme fibers. So the bending stress varies linearly across the depth. Now we can see the typical variation of bending stress across certain sections. So if it is a rectangular section, the neutral axis will be at the center and it will be maximum at the extreme fibers. So if it is subjected to a sagging moment, there will be tensile stress at the bottommost fiber and compressive stress on the topmost fiber. So if it is an irregular figure like this neutral axis will be passing through the centroid at this point and the variation of bending stress will be like this. Now in the case of a triangle, the neutral axis will be passing through centroid, that is at a distance of h by 3 from the base. So it will be like this, the variation of bending stress. So in all these cases, it can be shown that neutral axis lies in the centroid of the section. For that, you consider the force on an elemental area. You consider a cross section of a beam. Let this be the neutral axis. Consider an elemental area delta A at a distance y from the neutral axis. Now the force on this elemental area equal to let F be the stress on this elemental area. Force will be equal to stress into area F into delta A. Now what is the total force on the cross section of the beam? Sum of all the stress on this cross section, sigma of F into delta A. The total force on the cross section of the beam is sigma of F into delta A. So what is your equation for stress? E by R into Y. We have derived this. Substituting in this equation, we will get the total force equal to sigma of E by R into Y into delta A. E by R into sigma of Y into delta A. Now we know that the axis of the beam is not subjected to any force, so we can write this, equate this force equal to 0, but E and R are constants, cannot be 0, so we can write the sigma of Y into delta A is equal to 0. Dividing both sides by A, you will get sigma of Y into delta A by capital A equal to 0. Now what is sigma of Y into delta A by E? It is the distance of centroid from the neutral axis. We have measured this Y from the neutral axis. So this is equal to 0, which means that the neutral axis and centroidal axis coincides. Okay. So in all these cases, standard sections like rectangular section, you can locate the neutral axis as total depth by 2. In the case of a circular section, D is the diameter, it is D by 2, the position of neutral axis from the extreme fiber. If you have a triangle of depth h, the neutral axis will be at a distance of h by 3 from the base. Hence, the neutral axis coincides with the centroidal axis. Okay, thank you.